Okay, recording has started. So, we are at this lecture, deductive methods, and I go to in the large screen, and let me go to the end, because we were talking about groundwater, deductive assessment of groundwater resources. So we were here. So this is our control volume. Let me just get it in a, here it is. This is our control volume, and we are trying to build, as you may remember, because it was 1 week ago, an overall equation describing inflow and outflow from this control volume. And in order to do that, we apply the usual conservation laws of fluid mechanics, conservation of mass and conservation of energy. And we started discussing the conservation of mass. Conservation of mass, I go back to the web page. It's here. Here you see mass conservation. Basically, we refer to the control volume. Our control volume in this case is fixed. We take a portion of the aquifer and fix a control volume to study the aquifer. The control volume is, for now, it's infinitesimal. It refers to an elementary portion of space. And the reason why we refer to an infinitesimal portion is that we want to assume that the properties of the porous media are constant, are not changing within the control volume. So this is why we refer to an infinitesimal portion of space. Later on, we will need to study the behavior of the aquifer. The aquifer, which is the groundwater body, it's of course has a significant size. It's not infinitesimal. And therefore, in order to get to represent the whole aquifer, we will need to integrate the equations that we derive for the infinitesimal portion of space. So we build together, we sum up what happens in each single fraction of the aquifer. We build up all these elementary contributions. We sum them in order to get an estimate and assessment of the behavior of the aquifer. These conservation laws are expressed in differential form. Basically, they say that elementary change of our state variables, the variables with which we describe the aquifer, we set up equations that describe the changes of these variables. And therefore, if they describe increments, changes, then they are expressed in the form of differential equation. For instance, what you see here simply says that in the control volume, in the elementary control volume, change in storage is equal to flow in minus flow out. This is the elementary form of the mass balance equation or continuity equation. In fluid mechanics, it's often called the mass balance equation. It's often called the continuity equation. And then by describing the change of storage, we obtain the result that we describe both groundwater resources availability, storage, and also we describe flow in and flow out, which is recharge, flow in, and water resources withdrawal, flow out. Okay, now let's now develop this equation. We already discussed it. We refer to the elementary volume, and then we get the equation in the form that you see here. Let me go to here. and precisely here. This is the representation of Q out, and a similar equation can be written for Q in. So we describe Q in and Q out by referring to the components of the flow in the three directions of space, and we refer also to the changes of the three components along each one of the three directions. So let me just make reference to this is let me see if with the graphic table, this is inflow, and then this is change in inflow along the x direction. This is x. So if you sum up these two changes, this one and this one, these two components, you get inflow plus change in inflow along the x direction, and this is precisely outflow. The sum of the two, inflow plus change of flow in the x direction, becomes outflow. And then in order to get the dimension of a volume, of a storage, we need to multiply by the area of the flow, which is the y, the z. You sum up these three components. This is the second and this is the third, and then you get an expression for the outflow. And if you go back to, in fact, to my website, you see here, this is the inflow, which is just, I wait for a while because I think at least on my screen it is a bit slow, so I don't want to speak faster than the images on the screen. Let me just wait for a while. Okay, here we are. Let's wait for a while. I think it's at least my connection, it seems to be a bit slow. So in the web page you can see the expression for the inflow, which is just given by the sum of the flow in the three directions of space, and then there is here you see now it's selected, this is inflow, and then there is outflow, which is the equation that we previously derived. So if we substitute in the above equation, we obtain the equation that you can see. Let me see if I can do it here. Just I'm still waiting because I have a double screen and I see that it's quite slow. The change of the screen is quite slow. But in any case, let's say in words that if you substitute inflow and outflow in the above continuity equation, you get at the end of the story an equation in differential form which expresses change in storage as a function of flow in the three directions. I'm still waiting because I see everything slow. Can you please write on the chat if you can hear me well, please? Okay. Okay. Because I'm not sure you see the screen that I'm showing, but anyway. And okay, so everybody seems to hear well. And just one second, I need to make sure that you can see what I'm showing on the screen. Just one second, because I wanna. Okay. Can you now please tell me if you see a figure on the screen, if you see the red circle that I just drawn? Do you see a red circle in the middle of the figure? Okay. I see. So it's slow. Yeah, perfect. And also I got from Massimiliano a screenshot. Yeah, so the screen is slow. Let me try to disconnect it and reconnect. Just 1 second. Okay, now let me connect it again. One second, and let's see. Still, it is slow. Don't understand why today is like that, but it's probably because, you know, Monday morning, maybe that the connection is not that good. Let me check. Okay, let me try to wait just 1 second. Still very slow. I think you can't see my screen now. So let's assume that you don't see it. And let me try to speak. But I hope that you can manage to get the web page I'm referring to. And in the web page, basically, I am at the point where the text that I selected before, I'm just below that. And I'm still sharing the screen, but given that I can't see it on my second screen, I think you also can't see it. Okay, anyway, let's focus on the concept. We have this elementary control volume, and we need to describe the changes in storage. And the changes in storage are described, as far as we discussed now, depending on the flow in the three directions, depending on the change of flow in the three directions. Now, we have an equation that describes storage depending on flow in the three directions. And now, in order to get a more complete representation, we need to introduce a second equation that describes the change in storage, and you can see it if you go just down a little bit in the web page. There is a differential equation that reads like derivative with respect to time of W is, which W is storage, is equal to a term SS called SS, S capital S subscript S again. This is specific storage, which multiplies the change in time of the hydraulic head. And I already said what is hydraulic head. Hydraulic head is represents the energy of the aquifer body, the energy of the water body. It's precisely potential energy, because hydraulic head is the position of the water table. Hydraulic head is the water level that you reach into a well if you look into the well. You see a water level. The water level is the head, and therefore the head is potential energy. You may wonder why we don't consider kinetic energy. We don't consider it simply because kinetic energy is negligible in groundwater flow. I'm trying to share the screen again. So, as I said, it's the new equation expresses the storage depending on specific storage and change in hydraulic head. Now, what is specific storage? I think it is important, and we didn't do this focus last time, that I give more details on the specific storage. The specific storage, which is also called volumetric specific storage, it's the volume of water that an aquifer releases per volume of aquifer and unit decline in hydraulic head. So suppose that you have an aquifer, no matter if it's confined or not, and suppose that you decrease your hydraulic head. You decrease it of a unit decline. Now, by decreasing the hydraulic head, we want to estimate the amount of water that the aquifer releases per volume of aquifer itself. You may wonder, what are the processes leading to release of water? If the aquifer keeps saturated and the volume of the aquifer remains the same, because we refer to a unit volume, then the volume doesn't change. The aquifer remains saturated. Why is water released? What are the processes, again, leading to release of water? There are two components. If you decrease the head, you decrease the pressure into the aquifer, because remember that you have a column of water up to the level of the head that is pushing over the aquifer. So hydraulic head translates into pressure. As you go down, this energy of the water body, this potential energy is converted into pressure energy. If you go down, you have a decrease of potential energy because you decrease the level of water, but there is an increase of energy due to increasing pressure. Now, if you decrease the pressure on the aquifer, you have a release of water that is given, one, by the fact that you have expansion of water, two, the fact that you have a compaction of the aquifer. Because if you decrease pressure, then the aquifer gets compacted and there is a release of water. Like if you squeeze a sponge, it is more or less the same process. And again, you reduce the pressure of water, so you get the effect that the aquifer is squeezing, because there is the internal pressure that tends to expand it, which decreases, and this is the main component of releasing water. And then you may have a component, if you admit that water is compressible, there is a component due to expansion of water. This is explained if you go down in the page. I put a box. If you go down, there is a box which is within a rectangle, and inside the box you see that there is specified what is volumetric specific storage. I notice a spelling error into the box, so give me 1 second, I take a note. It's just the first word into the box. Okay. There is also the definition of another quantity, which is storativity, and which is related to volumetric specific storage. We don't need to go into this detail now. So let me continue referring to the previous equation. And still, I'm sorry that we still don't see the screen. Okay. Okay, let me do like that, because I really can't stand the fact that you don't see the screen. I changed the network connection. Give me 1 minute, and I'm staying here. Just 1 second. Because I have two connections, and let's try with the second one. The second one is used actually by my son to attend online classes, but I think he has today more bandwidth than me. So I usually use the hotspot of the phone, but today, now I think you can see my screen, so I think it's definitely better. Still, it says to me that the quality of the network is really bad, but I think at least I got it for now. Let me see if it's still working. Yes. Okay. Now you can see the screen, so let me go to the equation that I wanted to highlight, which is this one. And you see here we got the change in volume expressed as the product of the specific storage times change in hydraulic head, which is consistent with the definition of specific storage that I just gave. Okay, very good. Now we can substitute here, and then we can write the equation in this form. One second, let's wait for, here it is. We can write the equation in this form, namely the change of the flow components along the three direction of space is now related to the specific storage. So we eliminated storage from the state variables of this equation. So we remove the storage as a state variable, and the reason why we remove it is that storage is difficult to describe. So basically, while storage in a reservoir is easy to describe because you see, you can measure it, and also storage into a catchment is easier to describe because you can easily measure what is inflow, which is rainfall, and what is outflow, which is the actual river flow. So indirectly, you can estimate storage. When you refer to aquifers, to groundwater, estimating storage is complicated. It's complicated because just one second. I'm not sure you can listen to me. Okay, perfect. And so, as I said, storage is more complicated to describe into a catchment. So we devised this way to eliminate it from the equation through the introduction of the volumetric specific storage. Of course, you can understand that by introducing this quantity, you are not avoiding uncertainty, because basically you, just one second. Okay, here I am. Just one second, I need to share the screen again. Okay, let's try. You should hear me now. Okay, and you should be able to hear me now. Okay, works. Yeah, today it's, you know, you have to be patient with me. Today is a bit of a nightmare, but we have to manage in some way. And then I try to go back to the phone later on to check. But for now, let me try in this way. And as I said, I was discussing about the fact that by introducing the specific storage, we are not avoiding uncertainty. I mean, also there is a lot of uncertainty if we try to quantify the storage of a catchment. We still have a lot of uncertainty when we try to quantify the specific storage. We just substituted a massive property, an extensive property, with a local property. Okay, so this is the equation that we have to deal with now, and we can manipulate this equation a little bit, and you can see here the development, and if we simplify the equation by dividing everything by the x, the y, the z, we get to this form, which is simplified. Again, it's a direct relationship between the three flow components and specific storage and head. And look, also by introducing the head here, we introduced a variable that we can easily measure. Amazing. Okay, here I am. I realized when it broke the connection. I realized when it broke the connection. Yeah, I know. I realized when it got broken. So I'm still now I share the screen. I'm still at this point here. You know, we have to be patient. And today, in my limited experience with this situation, on Monday morning is the most critical time. So both the connections that I have are a bit lazy. And be patient. I'm sure that now you are listening to me, and you should also see the screen. Let me check if okay, perfect. Thank you. It's still a little bit unstable, but let's hope for the best. As I said, I was discussing the fact that we introduced also the head here, and the reason why we introduced the head in this equation is that the head is instead a variable that can be easily measured by looking at the water level into wells. Okay, now we have the equation in this form, so let's go back in compact form. You can write the equation in this way. So the divergence of the vector q, 1 second because it tells me that still the connection is weak. Okay, now we are back. So the divergence of the vector q is equal to the specific storage times changes in time of the hydraulic head. Okay, let me go back. The screen is frozen. Not really frozen, it's just very slow. Okay, this is also called, this equation that we obtained, divergence of flow equal to specific storage times derivative with respect to time of the hydraulic head. This equation is also known as the diffusion equation or heat equation, because it's the same kind of equation that is applied, derived to study diffusion processes or diffusion of heat. It is a parabolic partial differential equation. There is an extended literature on how to treat this equation. Now, what are the unknowns here? The unknowns are the fluxes, the flow Q, and the hydraulic head. Both of them depend on the three dimension of space and time. And if, as I said at the beginning, if we want to describe the flow in the aquifer, in the large body of the aquifer, we need to integrate this equation. However, the problem is a bit complicated, as you may understand, because we need to describe two variables, head and flow, depending on four independent variables, the three direction of space and time. What do we need to study this equation, to integrate this equation? We need to specify the initial and boundary conditions. But there is a more important specification that we have to make. Given that we have two unknowns, we need to couple this equation with another one. And basically, we need a second equation. Basically, what we did so far is only only what we did so far is only to apply the mass balance equation. This is the only equation that we applied so far to get to this stage. Now we need, as I said, a second equation, and the second equation must be the conservation of momentum, or if we refer to specific condition, it turns into conservation of energy. But let's focus on this second equation, momentum equation. It can be derived from the Navier-Stokes equations. But actually, this momentum equation was derived first experimentally by a famous hydraulic, a famous researcher on fluid mechanics, who was Darcy. Darcy derived this conservation equation experimentally, as I said, and then later on it was the same equation was mathematically proved. It was precisely derived from the Navier-Stokes equation. The Navier-Stokes equation expresses the general principle of conservation of momentum in fluid mechanics. Now, let's have a look at the Darcy's law then, which, as I said, it was derived experimentally and then proved mathematically. So the Darcy's law, you can see it just below in the form of three equations, one per each direction of space. And let me see if I can, one second, I'm trying to change connection again because for some reason I still have problems. 1 second. Okay. Give me 1 second. Okay, here we are. Let me see if you can see my screen. Just 1 second, because so far you... One second. Let me see if we can... Yeah, now you can see the screen. Okay, today is a nightmare. Okay, as I said, this is Darcy equation, which is expressed in the three direction of space. Look, this is an equation which relates flow to change in head. So it's an energy equation. It's a conservation of energy equation. When you relate the flow to a change of energy, you are applying a conservation equation, a conservation of energy equation in some form. Precisely in this case, it's conservation of momentum because it refers to vector of flow. So when we talk about a vector, then you cannot you cannot talk about conservation of energy because energy is a scalar. We have to talk about conservation of momentum, but they are strictly related. So when you have an equation which relates flow, which means a kind of change in energy, because flow can only occur if you fuel the flow with some energy. So when you write an equation relating flow to a change in head, as you can see here, this basically relates flow to a change in energy because head is energy. So it's an energy equation. And you can notice here that the dependence between the flow, which is also velocity of the flow, because when you talk about flow, flow is linearly related to the velocity of the flow. So when you can see here that change in energy is related to the velocity linearly. Usually in fluid mechanics, if you remember from your previous studies, it's the square of the velocity that is linearly related to change in energy. In this case, the linear relationship is between change in energy and velocity, not squared. The reason why here the relationship is overall linear is that the kinetic component of the flow is negligible. The reason is that velocity is very, very low, and therefore this leads, by neglecting the kinetic terms in the related physics, this leads to a linear relationship between velocity slash flow and energy. And as I said, this was derived experimentally by Darcy with a very simple experiment. And now it's applied in the three directions of space. And then we can substitute in our previous equation. Let's see if the screen is still, yes, it's still working. So if we substitute above, we get this equation, which is somehow even simpler, because now it relates, we have only an unknown here. It's only the head. And of course, this is simpler, because now we have one equation for one unknown. Of course, we are also interested in describing the flow, but once we describe the head, we can then describe the flow by using Darcy's law. So we didn't lose anything. We just got a simplified representation of only one variable, which is the head. And then once we describe the head, we can describe the flow in the three components through Darcy's law. So this is perfect, and we can write it in this more compact form. So K, what is K? Sorry, I forgot to say what is K. This is extremely important. K is hydraulic conductivity. It has the dimension of a velocity. Let's go back to Darcy's law here. This is Darcy's law. You see that on the left-hand side, you have a flow. Flow is, in terms of units, is cubic length divided by time. And on the right-hand side, you have it's an adimensional quantity, which is h divided by x, which multiplies k. Actually, on the left-hand side, this is specific flow. If you remember, it is specific flow. So specific flow, the dimension is length divided by time. On the right-hand side, you have the second factor, which is adimensional, and therefore we conclude that k has the dimension of a length divided by time. So it's a velocity, okay? It's a velocity, it's called K hydraulic conductivity. Usually it may depend on the direction of the space. Like I should have written here, if I wanted a more general representation, Kx, Ky, and Kz. But here I use only the symbol K because I assume that K is equal in the three directions of space, which means that the porous media is isotropic. So K is, again, it's a velocity, and it's the velocity of the flow for unit decline of head. So it's a typical behavior, inherent behavior of the porous media and the aquifer. And by knowing K, which is again called hydraulic conductivity, we can then compute, depending on the change in head, the velocity of the flow and the flow itself. Okay, so K is hydraulic conductivity, and then if we get back to our equation here, Now we have K, which multiplies squared divergence of H, which is equal to specific storage time changes in time of hydraulic head. Okay, perfect. Now, as I said, this is a very complicated problem. There is a first approximation that we can make. We can assume that the motion, the flow, is stationary. Stationary means that we don't have time dependence. We neglect variability in time. It's an assumption that is acceptable in most of the cases because the flow in the aquifer is very slow and therefore we can neglect it. And if we neglect the derivative with respect to time, we get to a simplified equation, which is this one. Oops, sorry, I made a mistake. Yeah, it's not an image. I just have to select it. This is the equation which is interesting to me. Let me deselect it. Squared divergence of H is equal to 0. This is also called the Laplace equation. It's used to describe many environmental processes. I'm thinking, for instance, about the sea waves. Can also be described by the Laplace equation. It's an equation that is well known. We know how to integrate it. It's an equation which describes a potential flow. What is a potential flow? It's a flow field where velocity can be expressed as the gradient of a scalar function. And in this case, the scalar function, which is called the velocity potential, is the hydraulic head. Now, mathematically speaking, it is a development that is not easy to follow, especially remotely, but just make an effort to focus on the concept. The concept is that we have here a measure of head, and you can measure it, for instance, by looking at wells. And this head is the velocity potential, meaning that I can express the velocity field by computing the gradient of the hydraulic head. It is very simple if you think at it. Like, I measure the hydraulic head, the level in 2 wells, and then I can estimate the velocity field between the two wells by just using the gradient of their levels. And this is something that is really interesting. I mean, it's really interesting because it gives a simplified view of the problem. Still, this is an equation that needs to be integrated and needs to be integrated because the porous media is not homogeneous. So we need to refer to infinitesimal spatial steps. Still, it's a complicated problem for which we have to define this list of items that are given in this list of bulleted points. The geometry of the control volume. If we want, we need to specify the material properties, including hydraulic conductivity. This is not simple, but still we can make some measures. We have to specify the initial conditions. Okay, the initial conditions can be the water levels into the wells, but still we have to specify them. And then we have to specify the boundary conditions, which means the level of the hydraulic head at the boundaries of the control volume. I mean, it may be easy to specify the boundary conditions. For instance, if the aquifer is confined, it's easy. but if the aquifer is unconfined, you need a lot of measurements in order to understand what are the boundary conditions when you start your modeling experience. And also we have to select a method of solution which can be analytical, numerical. So if it is numerical, you may also decide to consider the dynamic problem, variability also in time. But still, the problem is it's not easy, and very often in technical application we introduce simplifications. And the simplification is, if you look at this list of bulleted points, it's for instance the steady state flow is a simplification. And then we can assume that we have a negligible, this is an assumption that is frequently taken. We can assume that the vertical component of the flow is negligible. This is also called the Dupuit assumption or Dupuit-Forchheimer. I don't know how to pronounce it. It's very frequently mentioned as a Dupuit assumption. And this allows us to reduce to a two-dimensional problem. So if we assume that we have a negligible vertical component, we reduce to 2Ds. And then we can also take the 1D assumption, which is we can assume that flow is mainly along one direction only, and then we reduce to a one-dimensional model. This is the assumption that is frequently made in technical applications when one wants to compute, for instance, one wants to represent the dynamics of an aquifer which is mainly flowing in one direction. Okay, now there is a box here which talks about the volumetric specific storage, and what I want to say here basically is that I want to draw your attention on the fact that we still have a lot of uncertainty, and much of the uncertainty is related to the volumetric specific storage and also hydraulic conductivity. Both of them, hydraulic conductivity is not mentioned here, but both of them are properties of the aquifer. Both of them can be measured by making pumping tests. Okay, and please read this box. I'm not discussing about the definition of storativity now, because I don't want to give two definitions in one day only. It is very simple, and please have a read at it, because also storativity is an important property of the aquifer. So I really would like that you also focus on it, and but read by yourself. Okay, and then there is a discussion, a final discussion about the application of these models for estimating water resources availability. I propose to postpone this after a 15 minutes break, which we may make already now. Now the connection seems to work fine, and as I said, it's early morning of Monday. It's always a nightmare. And if you have any question, I give you half a minute to write on the chat. Otherwise, let's break for 15 minutes. Okay, let's meet again in 15 minutes. Thank you very much. Good. So we came to an equation, or let's say different versions of the same equation to represent the dynamics of groundwater bodies. There are now available several softwares to resolve this equation, because if we want to describe the dynamics, if we want to know how much water we can use from an aquifer, we need to resolve the equation. We need to resolve the equation under maybe simplifying conditions. We need to specify, as I said, initial conditions, boundary conditions, depending on the simplifying assumptions that we make. So we basically need, on the one hand, information. On the other hand, we need a software. So what are the main questions that we want to describe? First of all, the first question is to describe the distribution of the hydraulic head. This is in a way simpler than describing the flow, because the resolution of the equations is in a way it's simpler if we just limit ourselves to the head. And then additional questions are to describe how much water is there, which means how much water we can use from a given location. This is more than describing the head, because in order to describe how much water is there, you also need to describe the specific storage, and you need to describe the properties of the aquifer with more detail. Let me say that it's still an open question how we can use groundwater models with a sufficient reliability in order to support water resources management in practice. And the basic question is precisely related to sustainability. It is relatively easy to describe the distribution of the head. It is not as easy, and especially if you refer to steady state conditions, it is relatively easy to describe the distribution of the head. It's not that easy to describe how much water is there. As I said, it's still an open question, which has been solved only for small cases, only for cases of limited extension, for which we can indeed put into practice a very detailed monitoring campaign. We need to describe with a fine spatial resolution the hydraulic conductivity of the porous medium, the specific storage. This can be done if you set up a monitoring campaign with many wells and many pumping tests that can support a detailed definition of the aquifer properties. But on large scale, this is still an open question, because on large scale you have some regions where you don't have measurements, and therefore the question is how I can use like remote sensing information or modern statistical techniques in order to describe the distribution of the hydraulic properties for the ungauged regions, for the regions where I don't have any measurement. As I said, it's still an open question. There are ongoing research projects trying to describe the spatial distribution of groundwater resources at the global level, but it's something that is under development. And so far, application of groundwater models is, as I said, practical application is confined to limited regions. And there is also uncertainty. Uncertainty that whatever is the method that you use needs to be quantified, and the quantification is not that simple. Today we live in a period where we have the feeling that we can describe with precision whatever we want to describe, but actually this is not the case. There are several natural processes that we cannot describe with precision, and therefore uncertainty assessment is really a relevant issue. Okay, and now I think we can summarize what we learned so far in terms of deductive assessment of water resources, and it's we divided between surface water resources and groundwater resources, and we studied the basic concepts that can support a mathematical modeling of these components. The basic concepts are the same. In practice, we apply in few words, we apply conservation of mass and conservation of energy. The way we apply it is of course different. We refer to the catchment when we apply these equations to describe surface water. We refer to a groundwater body when we want to estimate groundwater resources, and in particular with groundwater bodies we need to refer to an elementary volume to describe, to set up the model, and while with the surface water we refer to the catchment very often has an elementary volume. It's also possible for surface water to describe the catchment by referring to elementary units, but it's also possible to avoid it. It's not necessary. It's possible but not necessary. And the reason why it's not necessary is that even if in a catchment you have spatial variability which is playing a relevant role, in groundwater resources spatial variability is much more significant, much more pronounced, much more relevant. And therefore in groundwater resources it's really difficult to make reference to the groundwater body as a unity. Usually we need to describe it by referring to elementary units. We highlighted what are the major sources of uncertainty. In groundwater resources, it's clear. It's the characterization of the aquifer properties. This is a problem because, as I said, heterogeneity is very significant, and therefore we need very specific monitoring campaign. For what concerns instead surface water resources, the main uncertainties are related to the spatial variability, and we highlighted that. Again, spatial variability of rainfall and catchment storage. Solutions for both the problems are mathematical models which involve parameters. These parameters needs to be measured or estimated in some other way. Like for groundwater models, the problem is to quantify specific storage and hydraulic conductivity. We need to refer to measurements, but we can also estimate them. In the same way as we estimated parameters for the iMod model, also parameters for groundwater models can be calibrated. And it's a solution that is frequently practiced and points out that model calibration, so parameter estimation, is a fundamental step of application of these models. So this gives to me the opportunity to introduce the next lecture. The next lecture is precisely, and let me go back to the web page of our course, and let's give it some time to show on the screen. The next lecture is precisely talking about, here we are now on the main page, it's talking about model calibration and validation. And I am now clicking on it. You see that it's underlined, model calibration and validation. What is calibration? Calibration is precisely parameter estimation for models. Calibration is another way to mean parameter estimation. So first of all, let's focus on the terminology. What is validation we will see later. Let me just now introduce calibration. And calibration, as I said, we need to focus on the terminology. And let me first emphasize that there are many synonyms for parameter estimation, one is calibration, the other one is optimization, and then we can say that the model is calibrated, parameterized, or optimized. These are synonyms. I am highlighting with the selection, but I still see that it's a bit late, so let's wait a little bit. And these are, as I said, synonyms. So when you hear people saying model calibration, which is the most frequent terminology that is applied, you just have to understand that it's a synonym of parameterization, optimization. And it's, as I said, a fundamental step. And there are two ways, two main avenues to carry it out. And the two main avenues are by optimizing model performances or through expert knowledge. Expert knowledge or measurement. Like, for instance, I'm taking a note because I want to add, after expert knowledge, I want to add plus measurements. Okay. Now, actually, expert knowledge may be a synonym of measurement because by measuring you gain your personal knowledge. So let's say that there are two avenues. One is numerical, like, okay, I have a model and I have a code that is running the model as we did in our exercise with iMod. We just ran the model to find out what is the best combination of parameters. So this is a numerical way. I may even ignore the process. Calibration, numerical calibration, is the same process, even if, no matter if you want to describe the growth and the number of potatoes, or you want to describe water resources availability. Calibration is the same process. You just run a mathematical model independently of the process that you are describing, and you find by numerical experiments the best combination. Expert knowledge, of course, is based on your knowledge of the problem, and by using your knowledge, which may derive from measurements, from observations, you guess the parameter values. Now let's focus on the first avenue, optimization of model performances. Let me say this lecture, it's not difficult. It's descriptive, very simple concepts, but it's important. It's a frequent question that I ask at the exam because first of all, I think it is a good question to assess if the student is prepared. And the second, as I said, this is a fundamental, even if it's easy, step in model application. And it's the step where the engineer really has to be creative, in making the best use of its knowledge. So, it's really when the engineer has to give its best, because usually model setup is done by others, and the numerical programming it's done by others. We need to know the underlying theory because otherwise we don't understand what they did, and we don't understand if the model is fit for purpose. But on the other hand, our specific job is precisely to adapt the model to the reality, is to apply the model, and therefore calibration is a fundamental step of our specific job. So let's focus on it. Here you see an hydrograph in this figure, and this is an hydrograph where you see the observed data with the continuous line, and the points and the dashed line shows you the model simulation. Actually, this is a very good simulation. Frequently, you don't get a as good simulation. And this is a real case. This figure is taken from a paper, from a scientific paper. Still, even if it's very good, you can see that the simulated hydrograph is anticipated by maybe a couple of hours, 3 hours. which is something that in some cases you really don't want. In some cases, for instance, think about real-time flood forecasting. It's not an application that is relevant to us, but think about that. If you delayed your simulation by 3 hours, it may be a disaster because you issue the warning when the flood is already gone. So it's this is to say that, for instance, even this simulation that looks very good, it looks good, but for some applications may be completely useless. Even if it's anticipated the peak, it's conservative, but still it may be a disaster, because if you predict a flood and give to people just 1 hour time to leave the home, when actually it turns out that they may have had 4 hours, it's a disaster, because if you give just 1 hour time, they may evacuate in a way that gives a huge economic damage, may also give some physical damage to people because they have to rush. And so even an anticipation is not a good thing. This is to say that when you calibrate a model and you assess model performances, you have to keep in mind what your application is. It has to be very clear what your final target is. And a good model for one application may be a very bad model for another application. So this highlights really the fundamental role of the engineer with a very simple example. Now, so let's discuss this calibration through optimization of model performances. There are 2 ways of carrying it out. One way is through trial and error. We did it. We already discussed it. No need to discuss it again. The second way is through automatic optimization. And we tried both of them. So we already know the pros and cons, because we already discussed, of the one and the other. The good engineer should make a good mix. And what I suggest is, if you can, try to make a trial and error by looking at each simulation in detail in order to identify the good set of initial parameter values. And this exercise allows also you to look into details of how your model works. What are the parameters that are more sensitive? So I highly suggest that an initial trial and error procedure is to be anyway carried out. And then when you find a good initial value for the parameter set, when you also found some indication about the boundaries, then you can run an automatic optimization. Now I want to discuss the metric that we used to assess model performances. We used this. Let me show this image. We use this sum of squares. Here you have with, I'm just waiting that you get it because it's still late. But if you scroll down the web page, okay, we are getting it. So here, f indicates the matrix. This function indicates the metric that we use to assess model performances, and we call it objective function. It's called objective function in the literature, and some contributions call it target function, but I think objective function is clearer, and it's the function that quantifies our objective. Here, f is a function of theta. Theta is the parameter vector of the model. And then on the right-hand side, you have the difference between observed xt minus simulated x hat t, which is difference squared. And then you sum over all the available data set, N here is the sample size of your data set. It's the number of observations that you have. Again, this is the sum. It's called sum of squares objective function, and we identify any method that makes use of it with the term least squares method. Now, this is justified by the fact the use of this objective function is justified by the fact, by the very technical fact, that we want to avoid compensation between negative and positive errors. So if you square them, you get this objective, you get to this target, and you convert any sign to positive. But there is also a statistical reason for using this objective function. Let me go back to the web page. Through statistical proofs, we can prove that this objective function is consistent and unbiased under certain assumptions. So let me also select under certain assumptions. What does it mean that it's consistent and unbiased? It means that it works well, in poor words. It works well. But let me discuss it in detail, because these are details that are related to theory of statistics, so we don't really need to go into the deep detail of this, but still I think it's important that we understand a little bit. And so what's consistency and what's unbiasedness? So what is consistency? There is a link here, and let's click on the link just to have a look of what it is. And let's see, yes, the screen should be, it works. And let me increase it. So let's just read the first sentence. In statistics, a consistent estimator, or asymptotically consistent, it doesn't matter. Let's say consistent estimator. Estimator of what? Of the parameter values, is an estimator, and between parentheses it explains what is an estimator, a rule for computing estimates of a parameter theta. So a consistent estimator is an estimator having the property that has the number of data points used increased indefinitely, the resulting sequence of estimate converges to theta 0. So it converges to the true value. What does this mean? It means that if your sample size of observed data increases, then your estimate converges to the true value of the parameters. This is very important, because if it doesn't converge, it means that your estimator is not really a good one. Ideally, you want an estimator that for a large number of observations gives to you the most correct value. This is consistency. And I think it is important that you learn this term, because frequently you will listen to people saying this calibration procedure is consistent. Keep in mind the significance. What does it mean unbiased? Let's click on the other link. So, in statistics, sorry, I want to increase the size. The bias of an estimator is the difference between this estimator expected value and the true value of the parameter being estimated. Okay? So you may think that it's the same thing. You may think that consistency and unbiasedness is the same thing. Actually, it's not precisely the same thing. If you want to inspect some more the difference between consistency and bias, there is a link here. I am just highlighting it, which you may look at. It is very interesting because if you click on it, there are some examples of estimators that are unbiased but not consistent, biased but consistent, and there is also the explanation of the conditions under which consistency ensures unbiasedness. And I also think that the term bias is extremely important for you because it's frequently used in statistics and also in the current language. When we say, for instance, that an approach is biased or a person is biased, I think it is important to understand what this means. So we can prove that the least square objective function is unbiased and consistent. And this is the concept that I wanted to highlight to you. And this justifies why it is so largely used. But actually, unbiasedness and consistency are conditioned by assumptions. There is written here, under certain assumptions, which, however, are rarely met in hydrological applications. So this is important to emphasize. Why it is important? Let me continue this discussion because I think it is relevant, and also I started it last time. I said, look, the least square objective function gives more weight to the flood simulation, to the simulation of high flows. You remember that I spoke about it last time, and I explained the reason, because squaring the errors, you give more weight to the larger errors, and therefore you give more weight to the simulation of high flows. If an estimator gives more weight to given river flow regime at the expense of another part of the river flow regime, it means that it's not unbiased. It's not consistent. A consistent and unbiased estimator should give to me some assurance that the river flow, the whole range of the river flow is well simulated, is well reproduced. The reason why least squares gives more weight to the high flows is that certain assumptions behind the demonstration of unbiasedness and consistency are violated. So you see that for application, it's certainly important to use your expert knowledge, but it's also important to understand from a statistical point of view what are the conditions under which your estimator, your model works well. And in fact, I write here, the sum of squares objective function is actually biased when applied to most hydrological models. And here, if you move forward, I say for rainfall runoff models, for instance, it's intuitive that it gives more emphasis to the fit of higher flows. This is what I just said. In fact, by squaring the error, blah, blah, blah. Okay. Now, what is the practical consequence for us? The practical consequence is that the sum of squares objective function is not the most appropriate solution for optimizing the fit of the low flows. So, and low flows are what are, it's what we are most interested in, because if we are interested in water resources management and water resources assessment, it's clear that we are more interested in the dry season, not in the high flow season. So what is an alternative objective function that we can use? Let me postpone this discussion. First of all, I want to show you this other objective function. This is based on the least square one. If you see the numerator of the right hand side, you see that it's sum of squares. But this objective function rescales the sum of squares. What you see at the denominator, it's the sum of the square differences between each observation and the mean. The over bar x is the mean value of our observations. So the denominator is fully independent by the model. Just 1 second, there is a question on the chat. So before, can you emphasize the reason why the sum of squares is not ideal? Okay, let me postpone the answer to you, just 2 minutes. I want to finish the discussion of this objective function that you see on the screen. So I was saying the denominator is fully independent of the model, it's just dependent on the data. It's something that you can estimate once you have your river flow data available, okay? Now, the sum of squares is rescaled by the squared differences of observations minus the average, and you see that this is given a negative sign, it is subtracted from 1. So let's look at the behavior of the subjective function, which, as I said, it's a rescaling of the least squares. If the model is perfect, what happens? If the model is perfect, you have at the numerator right-hand side, you have 0. And therefore, if the model is perfect, you get this objective function taking a unity value. Good. Now, what happens if the model is very bad? Let's suppose that the numerator tends to infinity. Then the subjective function tends to minus infinity. So the range of values for the subjective function is minus infinity to 1. It is helpful because as the subjective function approaches to 1, you get an estimate of model reliability, which is independent of the single application. And it's easier to judge. For instance, in hydrology, we say that any model that has a value of the subjective function that is higher than 0.85 is very good. And if the value we say is below 0.5, it's a model that is hardly useful. So you get a range of reliability of, let's say, optimal reliability, which is identified here without, it's independent of the specific case study. The sum of squares instead doesn't give to you such a independent and comparable measure of reliability. This gives to you a comparable between different case studies, among different case studies, a comparable measure of reliability. And let's say that, first of all, this is called, and you see the name in the web page, the Nash Sutcliffe efficiency. And let's emphasize a concept. What happens if this objective function takes a value of 0? It takes a value of 0 when, on the right-hand side, if you look at the ratio on the right-hand side, it takes a value of 0 when the sum of squares is equivalent to the sum of squared differences from the mean. What does this imply? How can you judge the usefulness of a model? I think one way to judge the usefulness of a mathematical model is, try to follow me on what I'm saying, is to compare the model with a trivial prediction. I mean, there are trivial predictions that we can make about a process. Predictions based just on our good thinking. If the model is not better than a trivial prediction, then I conclude that is It's not worth the effort. It's useless. What is a trivial prediction? A very good example of a trivial prediction is the mean. If I get a series of river flows, somebody asks me, what is your prediction for tomorrow? I don't have any other information. I think a trivial prediction is just to compute the average, the mean of the observation, and say my best guess for tomorrow is this, it's the mean. This is a very trivial prediction. And the result, the sum of squares from this trivial prediction is precisely what you see at the denominator on the right-hand side. So, if the squared differences of your model are the same order of magnitude of the squared differences from the mean, it means that your model is not better than the most obvious trivial prediction. So when you get an efficiency that is equal to 0, which corresponds to this situation, the model is useless. If your model gives to you some more of the trivial prediction, which means that the sum of squares is lower than the squared differences from the mean, then you start to gain some advantage. If the model gets perfect, you get to the upper value of reliability, which is 1. So I hope you can understand that even if the range is between minus infinity and 1 for the Nash-Sutcliffe efficiency, our range of interest is between 0 and 1. A negative value of the Nash-Sutcliffe efficiency means that the model is definitely to be thrown in the garbage bin. If you get a value higher than 0, you can start seeing some benefits from the model, but as I told you, up to 0.5 the benefits are really not that good. You start to see good benefits when the model is better than, the Nash efficiency is higher than 0.5. Now, there is a question. Can you re-emphasize on the reason why the sum of squares is not ideal for examining hydrological models, and also the Nash-Sutcliffe efficiency is not ideal? I mean, it may be ideal. It depends on what are the river flows you are interested in. Because then the sum of squares and the Nash-Sutcliffe efficiency as well, they give more weight to the larger errors because you are squaring the error. So it gives more weight to the larger errors. And the larger errors are found in the simulation of high flows. Because high flows, of course, being higher than low flows, lend themselves to larger errors, larger simulation errors. So it gives more emphasis, the sum of squares, to the high flows. Now, if you are interested in the simulation of the high flows only, this is fine. If you are interested in the simulation of low flows more than high flows, the sum of squares is not a good solution. Now, let me go back and let's introduce an alternative. This is very simple. If you take the sum of the absolute differences without squaring them, this gives more weight to the low flows because we eliminated the square. And this is another objective function that is largely used in hydrology. However, it's not consistent nor unbiased, which may be a problem, but still, I mean, if I am interested in the low flows, I can adopt it, and I don't care if it's biased or inconsistent, because I know that for the simulation of the high flows, it's not good. But I am interested just in the low flows, so let's focus on it. Okay, let's consider it, and this is a possibility. Another possibility is to consider the relative value of this absolute value, which leads us to the next one. The next one is this. Relative value of the absolute difference. You know, this objective function is another very good It gives even more weight to the low flows. It's another very good alternative. Keep in mind that it may be unstable, which means that if x tends to 0, you get values of individual relative errors that tend to infinity. So it may be unstable. It's not recommendable, it's not advisable to use it when you have x that gets close to 0. Okay, and then this is, I think, the last one I am considering. Remember these objective functions because they may be asked at the exam. And keep in mind that the literature proposes several other objective functions, and as you see written here. And some of them are statistically proved, meaning that they are proved to be unbiased and consistent. Other are not statistically proved, but as I said, we don't necessarily have to stick on a consistent and unbiased estimator. It depends on our application whether we want to stick on it or not. We may be creative in devising our own objective function. And so I think that there is ample room for creativity. We just have to be careful and very, very attentive, very careful about what we do by always keeping in mind the connection between the mathematical model, the real process that we are representing, and our technical target. Okay, very briefly, calibration through expert knowledge. I think we already discussed it. Please read by yourself these few sentences, and then we will talk on Thursday about model validation, which is another quite short discussion, but still, it's I want to take some time to discuss it because it's interesting and technically very relevant. Okay, perfect. Do you have any question on today's lecture in general? Let me go back to my webcam so you can see my face, hopefully. Okay, students, let's then meet again on Thursday morning. And meanwhile, as usual, if you have any question, please let me know. It's a time when I am looking at the chat every day, so don't feel relaxed. I'm always looking at you. Okay, very good. Thank you very much. Ciao, and let's keep in touch and see you on Thursday.